Great. It's week 10. I'm Breon. And this week, we're going to be talking about model results and reproducibility. Some topics for today. We're going to be talking about working with different model results. These are things like tidy model output with Broom, visualizing model effects with GG effects, tables with GT model summary and GT summary. We're also going to be I'm going to be on my soapbox talking about reproducible research practices and wrapping up the course. So let's start with working with model results. So thus far in this class, I've assumed that you have no statistical training, but I want to expose some of the best practices for dealing with models and statistics in R today. My favorite package for handling statistics is the Broom package. This tidies up the output from models such as LM, linear regression models, and GLM, generalized linear regression models. It has a small number of key functions. The tidy function that creates a data frame summary of a model. You could compare this to the summary function that's built into R, which creates a list of a summary of a model. We have the augment function. This adds columns such as fitted values to the data that we're using in the model, instead of having to pull them from our list object as we would in base R. And there's glance that provides one row of fit statistics for a model for, at a glance, checking model robustness and things of that nature. Typically, what we'll see is model output as a list. So if we use LM and summary, it produces a list as output, which cannot go directly into tidyverse functions, particularly those in ggplot2. So I've created some data here, and I run a linear regression model, and our summary will look something like this. And this object is a list. But model output varies. So each type of model also produces somewhat different output. So you can't just reuse the same code to handle output for every model. So using the same fabricated data, I'm now using a logistic regression. And we'll see that the things that come out of our list are not quite the same. So we have our deviance residuals here, rather than residuals, because they have a different name. We have different summaries of outputs from our model, things like our R squared versus no such thing for our logistic regressions. In comes tidy. Tidy produces a similar output, but as a data frame. So using our same model object from before, we pipe it to our tidy function. And we'll see that now, as a data frame, we have our coefficients, our standard errors, our related p-values. And each type of model has a slightly different method with its own additional arguments. So I would say look at the help for tidy.lm as an example. This output is also completely identical between models. This can be very useful and important if running models with different test statistics or running a lot of models, or if you like to make ladder plots or what have you, rock pots, and you want to be able to use the same code for different models and different sets of data. Glance produces data frames of fit statistics for models. If you run many models, you can compare each model row by row in each column, or even plot their different fit statistics to allow holistic comparison. So when we run glance on our linear regression model, we'll see that we get a 1 by 12 data frame with things of interest like our R squared. Well, if you're interested in the kinds of things like R squared, but things of interest like our AIC. Augment is really great in conjunction with these things. It takes values generated by a model and then adds them back to the original data. This includes fitted values, residuals, and leverage statistics. So we run augment on our regression object, and we'll see that it appends to our original data that was used to run the regression, the fitted values, the residuals, our sigma, our standardized residuals. There's a lot of different things you could do with all of this, and it makes it really easy to plot these kinds of things. So making fitted versus residuals plots in a modular way a lot quicker. The real advantage of Broom becomes apparent when running many models at once. Here we run separate models for each level of our factor variable in the fabricated data. So we take this example data and then we nest by. And nest by is going to create a list column for each of the levels that we handle nest by. And then we create a new column called model and run a linear regression for each of our new data frames per factor that we have. And then we can summarize the models in tidy from Broom. And we'll get a data frame that has, for each of our factors, all of the models run per factor. And this is way, way quicker than it used to be. When I was learning R, you would have had to subset the data, filter, maybe run a for loop here to perform this operation, and then run all of these things, and then create them all into one data frame. But now it's 3 lines of code. So let's talk plotting model results. And of course, this is great because no one wants to read your tables. One way that we've plotted model results thus far in this class is through geom smooth. I've used geom smooth in many past examples. Geom smooth generates smooth conditional means, including low S curves and generalized additive models. Note, however, that most regression models are conditional mean models, such as ordinary least squares that we're used to seeing, or any other sort of GLM model. That means that we can use geom smooth to add a layer depicting common bivariate models, but we wouldn't be able to hold all the other variables in a model at their mean, for instance. So I'll show you what I mean. We'll look at the Gapminder data from week 2. So if we use the default geom smooth, and we're looking at on the x-axis our year and on the y-axis life expectancy. I'm trying to think if there's anything else about this plot of interest to point out. Not really. But the outside of geom smooth. By default, geom smooth chooses either a low S smoother, where there's less than 1,000 data points, or a GAM, depending on the number of observations. And so we'll get a low S line through each of these, but it's only for our year and life expectancy variables. One thing that has been available to us thus far is to run a GLM for each of our groups by using method equals GLM and geom smooth and specifying the formula, which again is bivariate. We only have our outcome, life expectancy, and our covariate year. And with this method, we'll get a straight line through each of our groups. We can also specify things like squared or third term or cubed term by using method equals GLM and specifying our formula is y by, with that little tilde, poly, this helper function here, our covariate, and what the polynomial is going to be too. So this is a squared term, which means that we're allowing our lines each of our smoothers to have one curve in it. And this is like pretty nice if we're looking for maybe description. But we're often going to be working with more complex models where there's more than a bivariate model. What if we have a statistically complex model, something like a nonlinear probability model or a multi-level model? We have to go beyond geom smooth.
The vocabulary like polynomial and bivariate.
Sure.
It's not really relevant.
Totally. So for a bivariate model, that just means that there's two variables in it. So like here, we just have year and life expectancy in our model.
So multilinear regression or something?
Yeah, so if we ran a linear regression, that means that we only have the outcome and one covariate.
Okay. So you could have like more there.
Right. And then we would be having a multivariate model.
Okay. That's more than 5.
Yes.
Polynomial is complex.
Yes. So in this case, we're using a squared term. So our polynomial says that our relationship between x and y is x squared to y, and an x squared, a squared term will give us a parabola if we were like going to graph it. And that's why we're able to coerce a curve out of some of these lines. But we could also say like a cubed polynomial, which would allow us to have two curves in it, like when we were graphing in 8th grade.
It's like x minus y times x minus y, and then if you put all that out, it's x squared. That's a polynomial. Then graph.
Yes. But some more vocabulary. We are often interested in what might happen if some variables take particular values, often ones that are not seen in the actual data. When we set variables to certain values, we refer to them as counterfactual values or just counterfactuals. For example, if we know nothing about a new observation, our prediction for that estimate is often based on assuming that every variable is at its mean. And if that's kind of a lot of words, one way you could think about it is if we are going to get the height of everybody in our classroom, and then somebody else registers late, and we wanted to guess what their height was, we would just guess what the average of our classroom is. And we would probably be as close as we could possibly be using that average. When we construct counterfactuals, the logic is pretty similar, where we're using our model to look at the average across all of our coefficients and things to see across some dimensions what our y outcome would be or the height of this unknown person might be. We might have very specific questions which require setting possibly many combinations of variables to particular values and making an estimate or prediction. Providing specific estimates conditional on values of our covariates is a nice way to summarize results, particularly for models with unintuitive parameters, things like logit models, where our logistic regression coefficients are very difficult to understand as they are right out of the model. One great package for this is called ggeffects. I use it a lot. It's in my thesis. It's in a paper that I have out right now. It's awesome. If we want to look at more complex models, we can use ggeffects to create and plot tidy marginal effects. I'm saying marginal effects here, and I'm saying counterfactuals. Depends on who you ask whether or not these things are the same thing. For now, we're just going to talk about them as if they are. We're not going to get into all the semantics of it. That is tidy data frames of ranges of predicted values that can be fed straight into ggplot2 for plotting model results. We'll focus on two ggeffects functions. The ggpredict function, which computes predicted values for the outcome variable at margins of specific variables, as well as the plot.ggeffects function. This is a plot method for ggeffects objects that's like ggpredict output. Terrible typo there. And functions a lot of the same way as a ggplot. So this is some simulated data. To best show off ggeffects, I need a data frame with numeric and categorical variables with strong relationships. And it was easier to just simulate it. So here is some made up data. Now we can ggpredict. When you run ggpredict, it produces a data frame with a row for every unique value of a supplied predictor, that is an independent variable that we'll call a term. Each row contains an expected or estimated value for the outcome, that is our dependent variable, plus confidence intervals. So if we run a linear regression on a numeric outcome, given our numeric covariate and a factor covariate from our fabricated data, we can use ggpredict and the information from our model output across our covariate num1. If desired, the argument interval equals prediction will give predicted intervals instead. And it will look something like this. So it's saying across all of our values from our numeric 1 covariate, these are our predictions for what the y outcome will be for everything in the factor group A. And then we can plot them and talk about the content of our linear regressions across predicted values, rather than having to get into semantics of this coefficient is slightly larger than this one. Can we compare across these things? We get to talk about it at the level of the outcome across our key variable of interest. And this is really great. And it provides for A, like our research gets to stay on topic. I think it's really easy when you have a lot of tables for people to point out different little nuances of the table and lose the key relationship that you're trying to talk about. But with plots like these, you always stay on task, and I really enjoy that about them. If you ever take Chris Adolph's maximum likelihood class, a lot of it is geared towards this kind of statistical argumentation, and I find it to be very persuasive and useful.
Is that class like a class on maximum likelihood stats in addition to programming, or do you already have to know maximum?
No, it teaches you how to like write your own optimizations for different generalized linear models. Okay. And it also does a great job of talking about social science outcomes at the level that you'd be interested in them. So for instance, we might have like a count model where we're looking for the amount of events that happen as our outcome. And often it's the case that we might fit a Poisson distribution to that outcome. But in social science, Poisson doesn't happen all that much. And we'd rather be working with like a zero inflated Poisson or a negative binomial distribution. And the class talks about those things rather than the Poisson, but starts with the Poisson just to talk about them. So I find the class to be like incredible, but also highly instructive for social scientists.
So it's very like theoretical. What do you have to know before you take that class? Like I've already taken it again, and what is the regression and stats?
Okay, I feel like then you're good to go. Okay. Mm-hmm. Of course. We can also group using ggpredict. When using a vector of terms, ggeffects will plot the first along the x-axis and use others for grouping. Note we can pipe a model into ggpredict. So here, I fit a logistic regression and pipe it straight into ggpredict and give it the terms our num1, which we had before on our x-axis, and then also our factor variable. And it breaks up the factors and runs the same kind of predicted probabilities across that x-axis. And this is really great because now we are comparing the values at a level of one of our covariates of interest and across a factor variable at the level of our outcome. So we've managed to not just have a bivariate distribution or a bivariate model here all on one plot. And we can talk about the differences between green and red, for instance, and how blue overlaps with both. And it's great. We can also facet with ggpredict. You can add facet equals true to the plot and call to facets over grouping terms. It doesn't necessarily have to be with facet equals true. You can add a facet wrap like we're used to doing in ggplot. Facet equals true is often quicker. Let's talk about counterfactual values for a second. You can add values in square brackets in the terms equals argument to specify counterfactual values. So here, these values may or may not exist in the data, or might just be the ones that we're interested in. And so how that will look is you say what the variable is, and then in brackets, you can say from -1 to 0 to 1, or for factors A and B, and then it will predict from -1 to 1 for factors A and B what our values are given the rest of the information in our model. Do we have any questions there? It used to be the case that this was really time consuming to create plots like these. And now it's just like 2 lines of code and it's awesome. We can also predict using representative values. So we might use mean and SD or min max to set values of interest. For instance, if we look at our numeric variable for mean and 1 standard deviation, and our second numeric variable at its minimum and maximum. So this is for our minimum value of one of our covariates and the maximum value of one of our covariates. And we can make very strong comparisons very quickly. You can also make dot plots. You might hear folks also refer to these as like ladder plots. These will produce, for factor variables, they'll create error bars for categorical predictors so that we can look across factor 1 in our groups A, B, and C, and how factor 2 varies at each of these other factors, holding all the rest of our covariates at their mean.
So it's like the dot is the mean, and this is the spread, the standard deviation. And I never, like, I look at these, I don't really know.
Okay.
Like in the red, I know that's a simple question, but the red line, one of them, like at 1, the first one is the mean, and then is that the variance or standard deviation? Okay,
so here what this is saying is in our factor group 1, for that variable, we have a group called A. And people in that group are also in a different factor group called 2, which are yes or no. And for people who are in the yes part of factor 2, in the A group of factor 1, their predicted outcome is a 1, and the 95% confidence interval is this line.
Okay. So ideally, you want the confidence interval to be as small as possible, but I mean, well, it depends on the scale. But can you, so like the factor could be study time, and then group A, B, or C could be different ages?
Right.
That, okay. then you approve one of
Mhm. So notes on GGFX. There's a lot more to the GGFX package, and it's getting updated all the time that you can see in the package vignette and the GitHub repository. This includes, but is not limited to, predictive values for polynomial and interaction terms, getting predictions from models from dozens of other packages. I've been very pleasantly surprised with the minutia that this package can get into and predict well. And sending GGFX objects to ggplot2 to freely modify all those plots so that you're not dealing with like these base red and blue colors, and can organize them how you want in the syntax of ggplot. Yeah, really powerful tool. So I'm about to get started talking about making tables. Do we have any other questions about GGFX? Okay, making tables. We've used Pander to create nice tables for data frames thus far, but Pander has methods to handle all sorts of objects that you might want to display nicely. This includes model output, such as linear regression models, GLMs, and summary. For instance, you can send an LM object straight to Pander, and it knows what to do with it. So we have just our regular table here with our intercept, weight, and HP. Sorry, I'm forgetting what data set this was. You can also hand it summary, and it will put in the right place things like the number of observations that you had, the R squared and the adjusted R squared. Again, we're better than that. We don't need those. Let's talk a little bit about advanced tables. Pander tables are great for basic R markdown documents and are very instructive for thinking about making tables in R, but they're not generally publication ready. We're going to talk about a few different approaches for making nicer tables that won't be a cause for pause to reviewers. GT from RStudio for general table construction is very powerful. We're going to be talking about model summary for creating model tables themselves, and GT summary for creating data summaries. So GT, or general table, if you need more customizability or different output types, RStudio's GT package is a recent and powerful system for creating tables from data frames. We'll use dplyr's built-in Star Wars data for some examples. The Star Wars data is just a bunch of very nerdy things about Star Wars. And so I created this, the Empire Strikes Back characters data frame. Here I unnest to get rid of the hierarchicalness of our data and filter just to the Empire Strikes Back and select just the name, species, starship, mass, and height of different characters and keep only the specific ones. Again, you don't necessarily have to use distinct to deduplicate. And create a variable for starships, where if you don't have a starship, you get no ship. So we can take our Empire Strikes Back data and then pipe it to GT, and this is what it'll output. And this table on its own is a data frame. I mean, there's nothing really to write home about here, but GT is highly flexible and very quick about being specific about how you want your tables to look. And I think that it's stronger, better than the other table packages that are around. For instance, we could just group by our starships and then pipe to the GT, and it will go ahead and create its own line for each of these groups. So the X-Wing starship, the no-ship starships, the TIE fighter, Millennium Falcon, and so on. You can also specify row names, and this will get rid of a column name and divides the values from the measures to the right. So we've gotten rid of name up here because it's very clear to us that Luke Skywalker is a name. We can also quickly add headers and subtitles. So we've added Star Wars characters and The Empire Strikes Back using the tab header function. And already I feel like we're so far away from this first one that we had in terms of it being sort of publication ready. What publication, I don't know, but we can span over sets of columns. So here I've added the tab spanner function, the label vitals, and said for the columns mass and height. And we've added up here vitals under one heading. You can provide column labels just so that the things within the table have nice publication ready legible titles. So we've changed our data frame variable mass to mass in kilograms, height to height in centimeters, species to species with a capital S. You can format the numbers using the format number function. You can specify which columns for which you want to format the numbers and say how many decimal places that you want, which I find to be a lot more legible than a lot of the other ways that they describe formatting numbers. You'll note here that virtually all of the mass here is 0.0s except for Boba Fett's, which is oddly specific. You can also align specific columns. So here, using the calls align function, I said align equals center for the columns species, mass, and height. And note that down here, you can still call variable names from your original data set and that these are just labels. So you don't have to like type in the space kg. That's already looking so much more legible having these centered. You can also reorder the groups, perhaps in order of interest, by saying that we want our protagonist here at the top and the coolest ship right after that. And then guy who's only on screen for 10 minutes the whole series at the bottom. And this is a big improvement, and it can be done relatively quickly. These are great. GT is a fairly new package and is somewhat finicky when used in .pdf documents. So for tables in LaTeX, however you want to pronounce it, as is needed for a lot of .pdf files, I recommend also looking into Cable Extra, Hux Table, or Stargazer. Like GT, Cable Extra and Hux Table allow the construction of complex tables in either HTML or LaTeX using additive syntax similar to like ggplot2 and dplyr. Stargazer produces very nicely formatted LaTeX tables, but is idiosyncratic and doesn't support some models. And I find to be a lot of coding, and it's very nitpicky, and I don't like it all that much. It used to be all we had. If you want to edit LaTeX documents, you could use our Studio and Sweave documents. This is one of your options if you like go to File New. Alternatively, you may want to work in a dedicated LaTeX editor. I recommend Overleaf for this purpose. I also recommend Overleaf if you are looking to work in LaTeX even a little bit and are working with people. It's very much like working on a Google document simultaneously with others, where you can like type things together, that kind of thing. It's cool. It also is like Google Doc in that it saves very frequently, and so things can, moving tables around can easily be undone using Control-Z and whatnot. R Markdown has support for a fair amount of basic LaTeX syntax if you aren't trying to get too fancy though. If you want very specific things like, I don't know, 2 columns for your written part of your document, but also want the table in one to just be in one of the columns, but a graph to be partway through some of them and on top of the other table, those kinds of things, you might want to look into Overleaf for doing so. If only for peace of mind. You could do it in R Markdown, it just might take you a second. There's also the model summary package. This combines Broom and GT and Cable Extra to produce tabular summaries of almost any model fit in R. An advantage of this package is that it can produce output in every common format, so things like HTML, Markdown, LaTeX, raw text, or even as images, so .png and .jpg. Its key function is mSummary or model summary, which creates summary table of models. You can then build on it using either GT or Cable Extra functions, depending on the selected output format. And so that way it's very flexible, especially for collaboration. For instance, here, this is just the model summary of this model, which is the miles per gallon by the weight of the cars in the MT cars data set. It takes a model as an object, and then it makes it into a table. Note the default model summary looks like Pander tables because they use Markdown. You can present multiple models in mSummary using named lists. So here we've run 3 different models, all on the MT cars data set. This one's just a bivariate case. This one is a multivariate case. This one has an additional factor. And we then create a list of each of our models, and we can give it to mSummary, and it will format them the way you're used to seeing them in journals. This allows you to produce the common and often bad journal format where one starts with a nonsensical, naive model and works up to the full model that's justified by the whole rest of the paper. That's all that we're actually interested in. So why do we have this one here? Post-comps, I have a lot to say about all of these tables. Model summary is great for PDF output. You can say output equals LaTeX. This produces a Cable Extra based output that's well suited to PDFs. So here is that same table from before, but it looks a lot more like we're probably used to seeing in a publication. For customization, I recommend referring to model summaries documentation. It's pretty extensive. There's a lot of good vignettes of how different people have organized things in their tables. You can also save a model summary, doing things like mSummary, that list of models, output to a .png image, for instance. Do we have any questions there about model summary? That's right. You can select GT output to enable modifying summaries with GT functions. So things like we'll have a model summary on our model list the output is equal to GT. So that means it's going to be something that's recognizable to the rest of the GT package. And then we'll use tab header, and we can just use regular GT syntax to create different parts of our table that way. Note that GT's LaTeX support for PDFs is immature. This format is better for HTML or image output. It's kind of changing all the time, but I would still say that you might want to use the Cable Extra version of Model Summary if you're interested in PDF output. The GT summary package is similar to Model Summary in that it takes advantage of Broom and GT and Cable Extra to provide a flexible table making framework. While GT Summary can also produce model tables like Model Summary, it also produces descriptive statistics tables for data frames. I would say that I still prefer Model Summary syntax for most model tables and would only really use GT Summary for a table that is descriptive statistics that are maybe quick, but I also need them to look kind of nice. By default, GT Summary tables provide the frequencies for categorical and binary variables, the quantiles of the form 50% for continuous variables, and the sample size. So we can take the empty cars data that's built into R and then select the first 9 columns and then type that to table summary. And here's what we'll get. And we'll see that for each of the cylinders in these cars, 4, 6, and 8, it provides us with the frequencies. And for things like MPG, it provides us with the quantiles. You can provide a by equals argument to do group descriptives. So by factor variable, for instance, and it will quickly just decide to make 2 columns, but produce all of the same statistics. If you select GT as the output, you can dress it up with GT functions. So we have our table summary from the last slide, and then we pipe it to as_GT, and then we can span tabs for things like the transmission type, or provide our table headers with the same syntax as before for motor trend cars and descriptive statistics. You can also specify what kind of statistics that you want using the starts with stat underscore. I would say look into the helper for table summary to see more about that. One bonus thing that I think is really neat and pretty quick is the core plot package. It has functions for displaying correlograms. I only ever read that word. These make interpreting the correlations between variables in the data set easier than conventional correlation tables. The first argument to call to core is a call to core, the correlation function in R. And so here is a correlogram of that same data. And it's a lot easier to read than a lot of other correlation graphs and tables that we normally get. Yeah, it's neat because I really, these things are actually things that I'm only kind of interested in, but I can still clearly see that they're not really correlated. And then I can also really see which ones are highly correlated. It's nice. Okay, I'm gonna start talking about reproducible research. Do we have any other questions about descriptive statistics, tables, and summaries? Okay, reproducible research. Why? Why reproducibility? Reproducibility is not replication. These words often get tossed around as if they're the same. Replication is running a new study to show if and how results of a prior study hold. A good example of this would be Katz and Kruger in 2016 had this really interesting article about non-standard workers that replicates a lot of other studies about gig economy kinds of workers, but uses totally different data. Reproducibility is about rerunning the same study and getting the same results. For instance, in a couple of statistics courses, that's been my final paper, is reproducing a study.
You get new data.
With the same data.
So you wouldn't, like, if it's open source, you could just follow the steps.
Right. But I'd say in those classes, I didn't have the steps. So that was part of the puzzle of that project. But yes, rerunning the same study in TM and reproducibility is meaning getting the exact same things from along every step.
Okay. So, but if it's an open source thing and people like put their code, then reproducibility is like follow the code, but lots of people don't do that, right? So that's where this next is out.
Right. Yeah. And I don't know, it varies a lot from field to field, because I know that like for some journals, it's an issue in sociology where like not a lot of journals ask for all of your code for all of the steps. Mm-hmm. Right? They might only be interested in like the end part, if that much. Whereas others are like interested in all of the steps and right. And I imagine that there's a lot of like PII issues with education research as well. Like personally identifiable information.
Oh yeah. De-identify it, put it in, because you de-identify it when you put it in a spreadsheet.
Right. But I mean, if it's like about some people in a school in Los Angeles, I don't think it would be outside the realm of a data scientist's ability to match them back together at the end. Yeah. That's kind of a big problem with the census for 2020 is that they had to add a lot of noise to a lot of the things because for fear that somebody who was ill-willed and good at computers could match it back to people and do all sorts of perhaps. I don't know what you would do.
They made a lot of money.
Yeah, I guess.
You have robbing strong arm means violence. And remember strong arm
yes.
robbery? It's a threat of violence while you're robbing somebody.
Got it. Rather than just robbing. That makes a lot of sense.
Weapon, or you can say you have a weapon.
Right.
And that's called strong arm robbery.
Huh. Okay. And it's worse? Do you think? Okay.
I guess so. It's not just robbery.
I see. That makes sense.
Strong arm robbery.
Yeah.
So.
Well, good to know.
Yeah.
Reproducible studies can still be wrong. And in fact, reproducibility makes proving a study wrong much easier. And this is a good thing because we want to know the capital T truth. We want to produce knowledge. So reproducibility often means transparent research practices and minimal barriers to verifying your results. Any study that isn't reproducible can be trusted only on faith. Some definitions of reproducibility. Reproducibility comes in three forms. The first is empirical. This is repeatability in data collection. The next is statistical, verification with alternate methods of inference. This is often things like in the appendix. I also ran this model using a different setup. Third is computational. And this is reproducibility in cleaning, organizing, and presenting data and results. R is particularly well suited to enabling computational reproducibility. Python is equally well suited to do that. This will not, of course, fix a flawed research design, nor offer a remedy for improper application of statistical methods. Those are the difficult and non-automatable things you want skills in. Let's talk a bit more about computational reproducibility. The elements of computational reproducibility are shared data. Researchers need your original data to verify and replicate your work. There's also shared code. Your code must be shared to make decisions transparent and what kind of assumptions are just built into all of the steps. As well as documentation. This is the operation of code should be either self-documenting or have written descriptions to make its use clear. I do not like when I try to verify somebody else's results and I download the code from the publication and they're doing things that are not obvious and they have not commented anything in their code. And so I have to do a lot more work just to say, okay, yeah, that's the same thing they said it was. One good part of computational reproducibility is version control. This documents the whole research process as it's going on. And it also prevents losing work and facilitates sharing. Let's talk about the levels of reproducibility. For academic papers, degrees of reproducibility vary. The first one is often read the article. So I gave the example of I've reproduced papers that I read from this step, the read the article step. And it's very difficult to figure out where all of the data got filtered and what things they removed and what things they changed and how exactly they calculated each of the columns. If all you've done is read the article, and that's supposed to be sufficient enough information for other people to reproduce your research. Shared data with documentation. In my field, this is often where it ends. People just have the data available and say, these are the columns that I used, good luck. Shared data with all code is better, but maybe not optimal. I tried to reproduce a paper from Jake Grumbach in political science maybe a year ago, and he was nice enough to point out little nuances of the code and what things in his comments meant. That was a treat. It's not always like that.
Can you give an example of that? Like, I'm trying to have a long way to go, but they give you your code and they give you the data.
Mm-hmm.
Have the data set.
Yes, I could run it and I would get the same output, but I was interested in the under the hood, what was going on. So in that paper, Jake and his colleague Paul Freimer were looking at racial animus among people who are in unionized and non-unionized industries, and was able to find that people who are unionized were less inclined toward racial animus. And
like racial animus is like anger.
Right, just some amount of racism. It was kind of vaguely described on purpose. But the way that they did it was that they matched people who had very similar qualities along many, many different demographic kinds of information and other information, and who were in a union or not, and compared them. And I was interested in how that matching process worked because it seemed very black box to me when I read the paper. And so I was able to reproduce their matching, but I wanted to know more about how the matching worked. And so that's why it was nice that Jake was able to point out all of the little things about how the matching works.
Like the factors that they use to match.
Right. Because let's say that somebody's like, oh, well, I work and I make 45,000 a year. And then somebody who's in a unionized job says, well, I work and I make 50,000 a year. Those people might still get matched. But baked into the thing is that, well, the union premium is like exists in most industries who have unions. So are they really comparable if one's making 5K more a year and lives in LA while the other one lives in Charlotte?
Yeah.
Right.
Unions are supposed to, like salary is different.
Right. And benefits might totally look different. So I was interested in a lot of the like nuances with the matching. Of course. The next level of reproducibility is an interactive document. These are really great when you, I'm trying to think of a good one that I've read recently. I feel like maybe at the middle of the pandemic, Chris Adolph came out with a paper that was about different policies about the masks. And I feel like there was an interactive document about that, about the differences across different states and what policies were in place. And since you were able to like configure the models yourself, you could verify for yourself very quickly what they were talking about as their main thesis of the argument of their paper. And so that was really nice. The fifth level is a research compendium. I have not checked on one of these before. I know how they work and I know that they exist, and I've tried to make one and I thought it was too much work. But this would be something like a Docker image where you would save, in fact, the version of R that you had along with all of the data and all of the steps and document everything and make it interactive. And when somebody loads that other image, they would be loading like the exact version of the computer that you had basically, and able to run all of the stuff and see all of your steps throughout the whole process. I haven't encountered that in my case. Question.
So it attempts to like exactly replicate the condition.
Exactly.
Even processing speed?
Sorry?
Even like the speed that the process is?
That's a good question. I don't know.
I doubt it. I wouldn't.
Would it impact the results?
I don't think it could do that.
It might, because if it's an MLE and we have like one of those fake bottoms, I forget what it's called. Okay, so when you make an MLE and you're like looking for which parameters are best fit to our specification of the model and the distribution, there's a chance that the parameters that you find are not the maximum likelihood ones and we're actually at a sort of bimodal distribution where one's like a little bit taller than the other, but we think that this one's the maximum likelihood when it's actually this one. So processing time might matter. I don't know. That's a very specific case. Yeah, I guess I conflated 5 and 6. So this is a self-contained ecosystem that you could run on your computer. Interactive documents, things like R Markdown documents, combine code and text together in a self-contained document. That means they load and process the data, they run the models, they generate the tables and plots in line with text, in-text values automatically filled in, and so forth. Interactive documents allow a reader to examine your computational methods within the document itself. In effect, they are self-documented. By rerunning the code, they reproduce your results on demand. And should they wish, they could change something maybe at the top of the code and see how that changes the outcomes. Some common platforms would be R Markdown. There's a really wonderful example from the person who used to teach this class, Chuck, there, as well as Jupyter Notebooks in Python. Our research compendium is a portable, reproducible distribution of an article or other project. Research compendia feature an interactive document as the foundation. Files organized in a recognizable structure. So things like an R package. So someone could load the R package and it would have all of the sort of nuances of your own machine. There's a clear separation of data, method, and output. The data are read-only. A well-documented or even preserved computational environment, things like a Docker image. RR Tools by UW's own Ben Marwick provides a simplified workflow to accomplish this in R. I have not done it myself. There's another great example by Chuck. There's also Bookdown. Bookdown, which is integrated into RR Tools, can generate documents in the proper format for articles, theses, books, or dissertations. Bookdown provides an accessible alternative to writing LaTeX for typesetting and reference management. You'll note that in the course website, a lot of the documents that I suggest as readings are written in Bookdown. You can integrate citations and automate a reference page generation using bibtex files, such as those produced by Zotero Mendeley. Bookdown supports .html output for ease and speed, and also renders .pdf files through LaTeX for publication-ready documents. My friend Neil Marquez writes his papers in Bookdown. I think that's a little bit above my pay grade. For University of Washington theses and dissertations, I will plug again Ben Marwick's Husky Down package, which uses Markdown, but renders via a UW-approved LaTeX template. Okay, I'm going to get into talking about some best practices in organization and portability. Do you have any other questions about reproducibility before I move on? Sure.
Interactive documents, template, or research and
Mm-hmm.
So where would you include that? Like if you want to publish an article in journal, as part of my appendix?
Sure. Or you could say in your appendix, it's on my GitHub, right? Or you could say, like, depending on the journal, they might allow you to host a .html somewhere with like nicer looking plots, and you could include something like Markdown there. Okay, best practices on organization portability. Organizing research projects is something you either do accidentally and then badly, or purposefully with some upfront labor. Might not turn out that great, but it's typically better than if it was accidental. Uniform organization makes switching between or revisiting projects easier. I suggest something like the following. This over here on the left is going to be how the project folder is set up. And on the right, some descriptions of how it's working. First, there's a clear hierarchy. There's the project folder. There's a README that explains what the project is. And then there's the data and documents and syntax folders in that folder. And then there's some dependencies on the inside. The written content is in the docs folder, code is in the syntax folder, data is in the data folder. The naming is uniform, it's all lowercase, words are separated by underscores, or if you're a camel case kind of person, something that's uniform throughout, and the names are self-descriptive. I look at this and I say, I know what derived inside of the data folder means. And when I see that there's something called process data.r data in there, I'm aware what it means without having to really know what's inside. Same with core data inside the raw folder, inside the data folder, or paper.markdown inside the docs folder, or functions and models.r inside the syntax folder.
So would like the core data just be the data, and then the process would be like the cleaned data?
Right. Like the core data is just like the raw file, haven't done anything to manipulate the columns or anything. And the other one is the specific rows that I'm going to use in the models. Mhm.
Good idea.
I want to talk a little bit about the difference between workflow and the project. To summarize Jenny Bryan, one should separate workflows from projects. A workflow are things like the software you use to write your code. This would be like RStudio. Or the location that you store a project, the specific computer that you use, the code you ran earlier or typed into your console. And a project would be things like the raw data, the code that operates on your raw data, the packages that you use for that project, and the output files and documents. And you want these things to be separate because projects should not modify anything outside of the project, nor need to be modified by someone else or yourself in the future to run. Projects should be independent from your workflow. And this is valuable because we want them to be portable. For research to be reproducible, it must also be portable. Portable software operates independently of your workflow, which is the specific machine that you work on, such as fixed file locations. So I would recommend that you do not use setwd to set a working directory in scripts or .markdown files. Use absolute paths except for fixed and movable sources like secure data. So I recommend against using read_csv, c:, yada, yada, yada. Do not use install.packages in your script or markdown files, or remove list equals all of your objects. I forget what ls stands for, but all of the objects in your environment, anywhere but your console. I recommend using RStudio projects or the here package to set directories, using relative paths to load and save files, loading all required packages using library, and clearing your workspace when closing RStudio. I described it just a second, or forget when it was, maybe week 6. But you go to Tools, Global Options, Save Workspace, and you check the drop-down box, Never.
Wait, hold on. So I feel like I never clear my workspace. I really didn't know how to do it. So every time I go to R, like anything I've ever done, like good, bad, ugly, is like there. And
Right.
so I need to like change it so that every time I open R, it's like a clean canvas.
Yes.
So it doesn't mess with whatever I have.
Right, because you might have things change because of other things that were previously open or around.
Yeah.
Or
Yeah.
if you have 2 markdowns open and one is where your working directory is, that will confuse the other markdown sometimes.
Yeah.
We'd like to avoid all of those things. And also portability in general makes it so that, for instance, in conjunction with portability and my GitHub, it doesn't matter all that much to my ability to do research if someone steals my computer, right? Like that my workflow and my projects are separate. So like I would have to fix my workflow, but the project is still safe and works the same way. I recommend a divide and conquer strategy. Often you do not want to include all your code for one project in one markdown file. I was very guilty of this when I first started R, and now I see the light. Often this will make the code take too long to knit, and you'll get to the end of a project and you'll say, it takes me 15 minutes every time I want to knit, and I only want to change the header on the first part. Or the file is so long that it's difficult to read, and that all of the data processing, and then all of the model making, and then all of the descriptive statistics, and all of the graphs are all in one document, and it's just too much.
But if you have a faster computer,
Mhm.
that does help, right?
Certainly.
Yeah.
Certainly.
So like, not that I'm gonna go buy a better computer, but the best processor is always going to speed up that process, right?
It certainly will. But if you set it up so that each of those are separate steps in different documents, it'll still be far easier, even for somebody else who maybe has a slower computer to run also.
Okay.
There are two ways to deal with this. The first is to use separate R scripts or markdown files, which save results from complicated parts of a project, then load these results in the main markdown file. This is good for loading and cleaning large data, and then also for running slow models. So things like natural language processing that can often take a long time. This is really great. Two, you can use source to run external R scripts when a markdown knits. So you could have it set up that source runs a script when the markdown knits, and the output of that script then gets used later down in the markdown. This can be used to run large files that aren't impractically slow. Also good for loading project-specific functions. I find it beneficial to break projects into many files, scripts with specialized functions, or scripts to load and clean each set of variables, scripts to run each set of the models, a separate one to make the tables and plots, and then a main markdown that runs some or all of these to reproduce the entire project. Splitting up a project carries many benefits. Once a portion of the project is done and it's in its own file, it's out of your way. There's nothing more that needs to be done to it, and it's not something you have to scroll past. I don't have to Control F to remember where I was in my 4,000 line markdown. Instead, I just start at the top all the time. If you need to make changes, you don't need to search through huge files. So that entire sections of the project can be added or removed very quickly. Things like converting something to the appendix of an article, or if you get some new data, it's really easy to just put it in the beginning and run them all. It is the only way to build a proper pipeline for a project. So a bit about pipelines. Professional researchers and teams design projects as a pipeline. A pipeline is a series of consecutive processing elements. Scripts and functions in R might be where we're thinking that. Each stage of a pipeline, first, has clearly defined inputs and outputs. Second, does not modify its inputs. Third, produces the exact same output every time it is rerun. This means that first, when you modify one stage, you only need to rerun subsequent stages. Different people can work on each stage separately. Problems are isolated within stages. 4, you can depict your project as a directed graph of dependencies. Something like this. Every stage, which here is represented as an oval, has an unambiguous input and output. Everything that precedes a given stage is a dependency, and that something is required to run it. So here we have 2 data sets. They are input into the load data.r script, which then produces the full data.r data, which is then input into the reshape data R script, which then becomes the model data, which is then run by the models, which is then producing a table or a model plot, which go into the markdown at the end. Go back to this part. The full data.r data is given to the descriptives R script, which creates a PDF of a table, which goes into the markdown, and all of that gets taken together in creating a paper. Targets is a very recent update to a package that used to be called Drake. Targets is, I would say, the best practice for managing our research pipelines. As of now, I haven't used it a ton because I used to use Drake. I'm going to give some opinionated advice about tools, although all of today has been opinionated advice. On formats, avoid closed or commercial software and file formats except where absolutely necessary. Part of this is that it makes it very difficult for other people to reproduce your research and critique it and verify it, and that's a bad thing. Something that's proprietary that I see a lot. Sometimes, I would say SPSS still can output things that R can read. It can be a little bit difficult sometimes with SPSS because of the way that they label the rows and columns and things sometimes. But there are like, I'm forgetting the name of this particular software that a lot of people were using back in the day. But it would put out files as .dat, and these are very difficult to deal with and required that you use the same one or the same stata do file that they use in order to create it as a CSV. And it just seems like, well, you could have just made it a CSV and I would have never had a problem. So
it's like trying to open one of those Apple documents.
Yes, it's like that. Of course. Use open source software and file formats. This is always better for science TM. People should be able to explore your research without buying commercial software. You do not want your research to be inaccessible when software is updated as well. It is also often just better. It usually is updated more quickly. It tends to be more secure when something is in a very common format. And these formats are very rarely abandoned. Things like a .txt file that is tab separated is very old, and we can still use them just fine on all. Text file, just a. The ideal is use software that reads and writes raw text. Writing and formatting documents are two completely separate jobs. I highly recommend just writing first and formatting later. Markdown was made for this purpose. And I find that when I'm on a Word document, I often get caught up thinking, oh, it's already on page 3. I feel like I should skip this down and move this subtitle. Do those things separately.
So write it in Word, you're saying? You write it in Word?
And then transfer it? It depends. But I'm saying that a lot of traditional word processors would like you to format at the same time that you write. They waste time by leading you to formats instead of writing. Find a good modular text editor and learn to use it, something like Atom or Sublime, Emacs or Vim. Now, a little bit about version control. Version control originates in collaborative software development. The idea is that all changes that have ever been made to a piece of software are documented, saved automatically, and revertible. Version control allows all decisions ever made in a research project to be documented automatically. Version control can, first, protect your work from destructive changes. Second, simplify collaboration by merging changes. Third, document design decisions. And fourth, make your research process transparent. I feel like an example of the lack of transparency in a research project, or a highly transparent research project that I wish I had just seen the output of was, I don't know if any of y'all have read Judea Pearl's causality book. It's good, but it's written in the way that Pearl came to the conclusions at the end. So you get to watch his whole research process while he writes it. Oh, yeah. And yeah, it's just, it didn't have to be that way.
I read a book on how to read, and it was like, they don't do this, then they don't do this, then they don't do this, and they have a really hard time.
Right.
And like the end, I was like, you could have just told us.
You could have just told us the last part.
Right?
Yeah. Certainly.
Yeah.
But version control allows, if somebody wishes, they could watch all of those steps unfold as the project went on. Git is the dominant platform for version control, and GitHub is free, and now Microsoft-owned platform for hosting repositories. Repositories are folders on your computer where all changes are tracked by Git. Once Satisfied with changes, you commit and then push them to a remote repository that stores your project. Like this class and these slides were committed and then pushed this morning over coffee. Others can then copy your project or pull it, and if you permit, make suggestions for changes. And this is actually how our packages work. Somebody finds something that is slightly amiss, and they write some if-else statement that will fix it, and then they recommend that to, Jenny Bryan or Hadley Wickham, and they might accept it. And then the next time someone installs that package, it has that if-else statement inside. Constantly committing and pulling changes automatically generates a running history that documents the evolution of a project. And this is why I was trying to say in the beginning of the class that if you really wanted to work hard, you could find all of the keys to all of the homeworks on GitHub. Yeah. It's because the history of all of the times they have been pushed to the top of the website is there.
Wasn't that hard?
Great.
So you told me to do.
I did. And I showed you, I said where it was. So
I got it. It was awesome. It like hours of
certainly. Git is integrated into RStudio under the Tools menu. It does require some setup. You can also use the GitHub desktop application. I recommend doing that. I find that the Git that is integrated into RStudio is not my favorite. But the desktop application, I think, makes things very clear about where all of the stages are. But I also learned Git on the command line, so it's kind of tough for me when I have to just click buttons when I should just be to type them all. GitHub can also function as a CV. Beyond archiving projects and allowing sharing, GitHub also serves as a sort of curriculum vitae for the programmer. By allowing others to view your projects, you can display confidence in programming and research, and also some humility. If you're planning on working in the private sector, an active GitHub profile will give you a leg up on the competition. This is probably diminishingly true as more and more people are just using Git. If you're aiming for academia, a GitHub account signals some technical competence and an interest in research transparency, which is valuable all the time. And that was organizations and things. Do we have any questions there before we start talking about wrapping up? Cool. Let's talk about what you've learned, which is a ton of stuff, a lot. We talked about how to get data into R from a variety of formats, how to do data custodian work to manipulate and clean data, how to make pretty visualizations, how to automate things and vectorize things with loops and functions, how to combine text, calculations, plots, and tables into dynamic or markdown reports, and how to acquire and work with spatial data. So what comes next? You can work on statistical inference. So things like more C++ courses, functions for hypothesis testing and hierarchical mixed effects models, machine learning, survey design, are straightforward to use once data are clean. I think that you'll find that a lot of RA ships around campus are a lot of just data cleaning. There's also access output by working with list structures, things like regression models, or using Broom and ggfx. Also practicing, just practice. I also took this course, having not coded before.
Really?
Yes.
You didn't know anything?
No, I had played around with HTML on my MySpace, but that doesn't count.
Gosh. So similar to, I've done a little R, so very similar.
I'm sorry?
Like I came in with a tiny bit of R.
Mm-hmm.
That's where you were?
Yeah, I actually didn't know any statistics. I had not heard of Stata or SPSS. Oh, didn't use spreadsheets.
Look who you are.
I know, it was cool.
Like I would totally.
Wow, I appreciate that. I do not consider myself an expert.
How many, well, compared to, relative.
Yeah, that's true.
Well, how many years?
I took this class when I was a first year, and now I'm a fifth year.
So you just plugged and plugged and plugged, and now you know what you're talking about?
Yes, I did a lot of practice.
Yeah, I feel like I'm gonna have to retake the class as I watch,
Yeah, certainly. I still have on my like bookmarks bar of Firefox Chuck's class.
Yeah.
And I like refer to his description of things in the slides, which gives me like an older version of R sometimes, but that's okay.
It is so cool that you shared that because I didn't realize. I always feel like people are like started doing this in high school and it's like their other language, but I guess
No. In high school, I was playing basketball and flipping burgers.
me too. Okay, that's awesome. Yeah.
Ways that you can practice would be replicating analyses you've done in other things that you feel more proficient in, Excel, SPSS, data. You can think about data using dplyr verbs and tidy data principles. Next time you see a table, think to yourself, is this one value per row? R Markdown, writing things in R Markdown for reproducibility. This is really great if you take more CSSS classes to just try to start writing them all in Markdown. More advanced projects you might want to tackle, using version control in RStudio, interactive Shiny web apps. I would say getting good at Shiny would also be nice for a lot of RHA ships around town. And writing your own functions and putting them into a little package so that you can just run your own library so that you already have a negated percent in percent, for instance. I want to point you to a couple of neat things I didn't talk about at all because I thought it might be confusing. They've recently created a native pipe operator in R. It used to be the case that the mag reader pipes, like the percent greater than percent that we've been using, was the only place that you could get that in R. And now base R has its own pipe operator and it functions differently. For instance, let me say, what would be something that we might want to do? Let's say print. Okay. You could also say 3. Right? And this is slightly different in the way that mag reader pipes work, even though it looks the same. If we did this, okay, dplyr is not loaded. It's faster to do it this way.
Yeah.
And part of it is because these things are actually identical. Whereas what happens when you use the mag reader pipe is, remember that little dot thing that I said was magical and confusing, is occurring. And so these things being identical, these things are identical, but give you, they'll give you the same answer and use all the same functions, but are not exactly identical. I didn't talk about it because I thought it would be confusing and because it doesn't have a data equals dot kind of component. So where the information from the native pipe operator goes would have been confusing, I thought. There's also a source editor. So for instance, this is the homework 7. If you click this little thing here, this is a very recent addition to R. And it might take a little bit to load, but I'll show it to you. Okay, you can use this like Word. You can like change the background or like the headers and things by just typing them and changing the heading like this. And this is recent as in like the last year or so that you could do that rather than, and you can click around all of this stuff, rather than changing the actual underlying markdown document with different hashtags and things. It is kind of a pain. I think it adds more flexibility. And it's easier if you don't like to take your hands off the keyboard, which for me is true. Like I don't like doing this. But I know other people do.
Remember how many, like, I don't like exact remember, go look it up. There may be automated figure.
Yeah. I thought this would also be confusing to everybody when learning how markdowns work. If I just described it as it's like Word, but you can just kind of put code in. So I wanted to go the other way, which is the way that our markdown stuff. Here is just a list of like a bunch of keyboard shortcuts. I didn't describe a lot of keyboard shortcuts except for maybe Control-Shift-M and Control-Shift-K. Maybe Control-Option-I. But there are a ton. And so I'd say this is worth looking at. It's just somebody from the RStudio subreddit put them all together, all the ones that they could name. So here's an interesting link. It's called The Big Book of R. It is also written in Bookdown. It is your last ever bookmark. It's basically all the other Bookdown written big textbooks for R, and they're all in one place, and they're all like put together. It's pretty cool. And when you want to just be able to look up something very quickly, like, oh, I'm in social science and I want to look at census data, or some sort of, however people in public policy are doing things now, ANES data, what have you. It's kind of all there. This one's really great if you're learning statistics.
Oh, I saw that one.
Yeah.
I think I tried that.
But I didn't explain all those things, partly so I didn't scare anybody or kind of lead anybody astray, but they exist, they're there, they're cool. Some plugs for courses. If you have no stats background, recommend SOCH 504 and 505, 506. It's a little sequence of statistics things. And it starts from like frequencies and modes and mean and median and ends on things like, trying to think, what did it end with? First differences, plots, and that kind of thing.
The first difference was a DRT test?
A first difference would be, okay, I'm trying to remember what the name of the outcome is. I don't use them in my research. Okay, but it's a way of looking at what the effects of your covariates are on a set of groups as your outcome. Yeah, so it's under the umbrella of GLM methods.
Okay, I haven't taken that class.
Okay, okay.
Yeah, that's
Got it. If you've only finished SOCH 506, so like you've done that stat sequence, for instance, highly recommend Maximum Likelihood. I was talking about it earlier. I think it's just like an incredible class. It's kind of difficult if you don't know any R. A lot of people in my department warned me about that. So that's why I ended up taking this class when I was a first year, was so that I wouldn't just like be sad and trying to learn R while also learning these like stats things in MLE. But really great class and really teaches you a lot about GLM. If you want to master visualization, there's also 569's visualizing data class, which does not approach a lot of ggplot things. They're happy if you work with ggplot, but it actually uses other R packages for making really great plots. Great class. I love that one. If you study events or durations in any way, event history analysis is really great. And it's also a great introduction to maximum likelihood and how that works. What I was talking about earlier when I was saying, you know, when you have like the bimodal distribution, the one's like a little bit higher, but you actually got this one and you wanted this one. It does more of explaining what I'm trying to describe with my hands to a microphone. But and I don't know if Daryl Holman still teaches it, but when he did, it was awesome. Highly recommend. There's also a really great event history analysis book. That's one of those like blue cover for social scientists books. That's great. If you want to use network data, I'm pretty sure Tyler McCormick still teaches social network analysis. It might be at Roshava. Highly recommend that one as well. If you want to work with spatial data, I'm not really into spatial data, but John Wakefield teaches spatial statistics, and I only ever hear great things about that course. Highly recommend as well.
What's spatial data?
So let's say that we spatial as in like we're interested in comparisons between counties or
Okay.
or some other units. John Wakefield's especially good at doing statistics where there are very sparse data for spaces.
That's cool.
And yeah, certainly. And if you want to work with time series, which I assume lots of you do, the time series and panel data class is also excellent. This one, and what's time series?
Like file 1, file 2.
Time series is any sort of like successive set of questions that have been answered the same way. So like in time. So like even if it's like a general social survey thing where like different people answered them, but they ask the same questions, so you can compare across time. Whereas like panel data is what you're talking about, where like the same people were dealt with. Yes. And that's it. That was intro to R. Thank you all so much.